I'm going to present a talk that has to do a little bit with theoretical biology, and I will present some data that support what I think it's an interesting hypothesis. So in my group, what we are doing is research in the evolution of species, and we pay attention to three traits that were highlighted by Darwin: moral sense, aesthetic perception, and the evolution of language. In my case, I'm studying the evolution of language, and because evolutionary theory of species largely relies, in a broad sense, in biology and physics, and many approaches to the evolution of cognition also follow these steps, we frame our work also in biology, or taking into account what has been discovered until now in biology and taking interesting tools from physics. Of course, we also check what has been said in linguistics. Here we have Noam Chomsky, but we could add Tomasello, or we could add other languages. I mean, it's just one of them. So this forces us to read about genetics, theoretical biology, linguistics, and then go back. And we try to match what has been said and what has been discovered in both fields in order to push and to go in the right direction. So evolutionary theory and cognition, is this possible? We think so. And here I'm going to talk about the phenotypic space proposed by Alberch, which has recently been introduced in linguistics by Vallari and Lorenzo under the form of computational phenotypes. And I'll show data from studies on complexity, language, and language ontogeny, and networks that this seems to be a promising hypothesis. Now, the basic idea put forward by Alberch is that genes are not all. What we need something more in order to explain variation within species, but also between species. So, depending on the perturbations that affect the system could yield phenotype A, B, or C. What he proposed is a phenotypic space for different kinds of morphology. So here, for example, we see different sets of phenotypes. Yeah? And a species could develop one or more phenotype within a set. And another related species perhaps develops the phenotype, one of the phenotypes within the set of B. As the time elapses and the species evolves, the species could move within the set, and this would be considered linear progress, linear change. But at some time, at some point, and at some generation, the species perhaps is at the border of one of these sets. When this happens, at some generation, it could make a leap to the next set of phenotypes. And this is therefore that we can account for linear evolution, but also for those apparent gaps between species. An interesting aspect of this proposal, of this hypothesis, is that it accounts also for possibilities that we find in biology, but that most of them are at odds with life. These possibilities are in the apparently empty space. So in fact, there is no empty space at all. All these sets represent typical development, typical phenotypes, and sometimes when there is a deviation, and it falls somewhere here, is when we find examples like this. This example, for example, phenotype A can be found in all chordates. All chordates, all species that have spine, could develop a phenotype like A. or D. And therefore, we find once and again cows with 2 heads, cats with 2 heads, and humans with 2 heads. What we won't find, for example, is 50% snake, 50% Homo sapiens. So the application of this way to see variation, according to Per Alberch, can be applied to phylogeny, but also to ontogeny. For example, think in the descent of larynx. The larynx position in babies is very different than the larynx position in adults. So there has been a change in a considerable short period of time. Or think in a worm that becomes a butterfly. Yeah? So there are changes that can be considered linear, continuity, and then abrupt changes. That would be discontinuity. Now, this idea has been recently been introduced, as said, by Valerio and Lorenzo into linguistics. We try to put at the same level what they call the faculty of language, but more particularly the computational system. So they consider that, for example, Chomsky's hierarchy of languages, which are which have differences between grammars, are different regarding the computational power they have, could be considered as different phenotypes. And, for example, some animals that perform strings of, let's say, well, not symbols, but sounds that can be described by a regular system, perhaps it's here or here, and at some point the Homo sapiens species perhaps made a leap to a next phenotype. And it is therefore that we see continuity regarding some traits, regarding some characteristics in great apes, but then we see a huge difference between the computational power of Homo sapiens and the other 4 great apes. But the thing is that, is this applicable? How can we test it? Because brain, we know very well, doesn't fossilize. We have almost no clues about other hominins, and data from apes perhaps are too distant. So if we cannot test it directly in phylogeny, perhaps we could try with ontogeny. What we need is linguistic data from children, longitudinal studies, and proofs of qualitative differences in the levels of complexity. And it would be desirable to find proofs of sharp transitions too. And this is what we did. First, Korominas Murtra et al. Made a first work in which English was analyzed, and then we have replied it, including Dutch, German, and Spanish, in order to see whether the results found in the first work also happen to be the same, regardless the language. And now I'm working in Catalan, but also other atypical examples of the linguistic development, like specific language impairment and Down syndrome. What we did is we took many corpora from Child's database, and we analyzed each utterance or each sample of production of the children, and we analyzed the sentence, let's say the sentence, according to the very basic lines of dependency grammars. So, wil je ook nog appeltje? Here, appeltje depends on nog depends on wil, je, and so on and so forth. When we have a corpus analyzed, what we do is to extract a pattern. And we make this by means of a program which transforms all these sentences in a network. There are no, in this case, we do not consider how many times the child said appeltje. There is only one note, appeltje, which has a relationship, a syntactic relationship with the adjective letter of with the verb kijken of with the word nog. Yeah? So when we did it, this, for the moment, we have 5 languages analyzed, 6 children, and in the case of SLI, we have 12 children, and in the case of Down syndrome, for the moment, we have 2 children analyzed. These were the results. We find 3 different kinds of networks which represent, according to physics, 3 different levels of complexity. In the first case, 2 years and 2 months, and 2 years and 5 months. This was Dutch in this case. The first is known, is called tree-like network, scale-free network, and a small world network. There are differences in the topology and the parameters that physicists consider relevant for each case. And, for example, in the work we replied, we had 17 networks, and what we saw is that after a linear period of growth, there is an abrupt change to a scale-free network, then again linear growth, and then again an abrupt transition to the small world network. This is the same network, but with another perspective, and so we can detect the most important hubs in the network. In all languages so far analyzed, these hubs are functional words. You see, here is the growth of words and syntactic links. First, there is a linear growth, more or less the same words than syntactic links, and then there is a non-linear growth until the number of syntactic links is two times the number of words. And in all languages so far analyzed, happens the same. So, and this is what we have when we look at the to children affected by a specific language impairment, round dots, and Down syndrome. This is the scores they got regarding number of nodes which are equivalent to words. And we see here the 3, let's say, phenotypes, but simply let's say the 3 levels of complexity. This represents the first time we detect this kind of networks. Of course, there are other sublevels. Other networks of the same kind would be put between these 2 sets. And this, for example, look at here, the round and blue mat has almost the same score regarding the number of words. But when we look at the number of syntactic links, there is a difference, an important difference regarding the typical development of these 4 languages. For the moment, all affected members by specific language impairment are English speakers, and in the case of Down syndrome are Dutch speakers. When we look at the ratio, we see that the typical development begins more or less in 1. We start having or seeing the same number of words than the syntactic links, and it develops rapidly towards 0.5. Instead, the affected members don't reach this value. And when we see RODA, for example, which is close, we have to take into account that the ratio is not all, because RODA, for example, has a little bit more than 200 syntactic links. I mean, the ratio could be confusing sometimes, but in any case, the typical development is like this. So, what did we find? We have detected 2 different regimes of growth or development. First linear, then nonlinear. We have found abrupt transitions between the different kinds of networks, which represent different levels of complexity. And we have also detected deviation in the development in the typical cases. So it's not that the SLI or syndrome Down children developed or are frozen. It's not a frozen stage, it's a deviation, it's completely different. When we look at the hubs of the networks, we see that there are clear differences. For example, the typical hub in English is it. It is a word that has many, many, many connections, and it's completely marginal in the case of the SLI affected members. So, that was, I've been quick. Thank you very much.